All right, so today we are going to start on section 3.1. Okay, and this covers the definition of a derivative. Oops, glare off, that may be a little bit better. Now, we kind of looked into the main idea of a derivative in the preview section. Of course, I ran out of pencil leads. Give me 1 second. There we go. Okay, we kind of touched on it a little bit when we did the move the points closer to each other. Okay, so if you remember when we did the experiment here and we had the 2 points on the line, and this was at a point x and x plus h, and this value was f of x, and this value was f of x plus h. You move that over a little bit. And of course, someone moved my cards I use as my ruler. Let's see, I should have another one in here. There we go. And if you connect those two lines, this line is your secant line. Okay. So we went over this kind of in a little bit of detail in the review section. Okay, where the distance between these 2 points is just h. So you can always think about just regular numbers. Let's say x is equal to 5 and x plus h is equal to 8. This is just 5 and 5 plus 3, which is 8. So that distance is always going to be that h. Okay. So then if we move x plus h closer and closer, so we get this point and just keep moving it closer and closer and closer and closer till it's almost infinitely closer to x. And it's getting closer and closer than that. Okay, so we just go ahead and move x plus h closer to x. Okay, so if we do that, then you'll have the very same graph but your x would be right here. And your x plus h, I'm going to give it a little bit of space, but just imagine it almost infinitely close to it. So if it's almost infinitely close to it, they're going to be like almost at the same point. So x and x plus h would be right on the same point. It's like trying to separate 5 and 5.000. And let's say you have 30,000 zeros there and a 1 at the end. Trying to separate those, it's very little room between the two. So this is what we have here, two numbers that are just very close together. So if you have two numbers that are very close together, when you draw their secant line, you're basically drawing a line through one point because they're just that close. And that is your tangent line. Or your instantaneous rate of change. Let me separate that N and S a little bit. Instantaneous rate of change. Now, before, what we did was we would just make our box up and we would plug in values closer and closer and closer, which is okay to get an estimate. But when we're talking about getting a more precise value, we actually have to close the gap between those two x and x plus h as much as possible. So we have to get h as close to 0 as we possibly can, and even closer than that. So what we're going to do is we're going to take the limit as h approaches 0. Actually, we can start off with x plus h approaches x. Then we can go to that one. So x plus h is going to approach x of f of x plus h minus f of x all over x plus h minus x. Remember, that's just your difference quotient. We're just taking the distance between that and bringing them closer. Or you could rewrite this as the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, sometimes, depending on the notation or the problem you're solving, you could also write it as the limit as x approaches x sub 0 of f of x minus f of x sub 0 all over x minus x sub 0. That's if you know the value of x sub 0. That's when that's normally the best one to use. But if you don't know the value of x or your first point x or x sub 0, then you'd use this one. I mean, you could use this one whether you know the value of it or not. It's just that when you know the value of x sub 0, this is usually the faster one. All right, anyone still writing? Okay. Oops. Okay, so we know that our limit of f of x plus h minus f of x all over h, as h approaches 0, we just write that as our derivative. Okay. Now this just reads as f prime of x. Or the derivative of f with respect to x. I'm gonna get a little bit bigger. There we go. Okay, now when we have just a regular function, f of x, we just call that our position function. Because if you have x equals 2 and you plug it into the function, that tells you where on the xy axis that particular point is. So it gives you the position. Okay. Whereas our derivative, that gives you the rate of change at that particular point. That's called our velocity function. Clean that A up a little. That's the rate of change at x. Okay. Now, sometimes your velocity function is notated as v of t. Nope, not v of t, v of x. Or, in most cases, when they use the velocity function, they use t because that's with respect to time. But you can use the x. Okay, so a lot of these we're going to solve using the limit definitions. So let's say, for example, if we wanted to find the correct limit definition for the derivative of g of x is equal to the square root of x plus 1. Okay, Okay. We're not going to solve this one. We're just going to put it in the correct format. Okay. Well, we know the limit definition is just right up here, but instead of f of x, we're going to use g of x. So in this case, it's the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay. Now the g of x, we already have that. That was given to us. So we'll make that little box there. So we know that g of x is just the square root of x plus 1. Now g of x plus h, we're just going to replace x with x plus h. Actually, kind of go right there. Replace x with x plus h. So instead of x square root of x plus 1 squared, that's the square root of x plus h plus 1. So that means our limit definition is the limit as h approaches 0 is g of x plus h. Let me clean that up a little. There we go. So our g of x plus h is just the square root of x plus h plus 1 minus g of x. So minus the square root of x plus 1 divided by h. Okay, so that would be, for this one, our answer. That's the limit definition of g of x equals square root of x plus 1. All right, anyone still writing? Okay. So let's say if we are given the function g of x is equal to negative x squared plus 3x. What is the correct limit definition for g prime of 2? Okay, so we know that our limit as h approaches 0, g of x plus h minus g of x all over h. That's our g prime of x. So again, first thing we have to do, I already know we're given g of x. And that's negative x squared plus 3x. And our g of x plus h, we just make this, instead of negative x squared, it's negative x plus h squared. Plus, instead of 3 times x, it's 3 times x plus h. Okay. So just to simplify it a little bit, we're going to distribute that 3. And most of the time, they don't make you factor this one out or expand it. Okay, so you can sometimes leave that the way it is. So that's just negative x plus h squared plus 3 times x plus 3 times h. Okay, so we have our g of x and our g of x plus h. So now we're just going to get that and plug it right on in. So our g prime of x is just equal to our g of x plus h, which is negative x plus h squared plus 3x plus 3h minus your g of x. So that's minus negative x squared plus 3x all divided by h. Oh, forgot my limit, which is really easy to do. So it should be the limit as h approaches 0. There we go. So technically, without that limit, it's just the difference quotient. So you need that limit to show that you're talking about the actual derivative. Now, whenever you have more than one term for your function, your f of x or g of x, I do recommend the parentheses because you're subtracting that entire function. So if you do the parentheses, you can remember that you're supposed to distribute that negative to each term. So that means your g prime of x is equal to the limit as h approaches 0. Since this polynomial is positive, we can just drop the parentheses. So negative x plus h squared plus 3x plus 3h. You distribute that to negative x squared, you get positive x squared minus 3x all over h. Okay. If you notice, 3x and negative 3x or minus 3x, they add together to equal 0, so they disappear. So that gives us g prime of x is equal to the limit as h approaches 0 of negative x plus h squared plus 3h plus x squared divided by h. Now, once you find your derivative, find the derivative at 2. So to find g prime of 2, we just replace x with 2. Mouse out the way. Okay, so that gives us g prime of 2 is just equal to the limit as h approaches 0 of negative 2 plus h squared plus 3h plus x squared. So we replace that and becomes plus 2 squared, all divided by h. So just simplifying that 2 squared, our g prime of 2 is equal to the limit as h approaches 0 of negative 2 plus h squared plus 3h plus 4 divided by h. And if you wanted to, you could replace the 2 plus h squared with 2 plus h times 2 plus h through the FOIL method and then cancel out further than that. But you don't really have to. Both would be correct, but doing this is just a little bit easier. All right, any questions on that one? All right, I'll leave it up for a little bit. Let everybody finish writing. All right, anyone still writing? Okay. What if we want to find the slope of the tangent line of f of x is equal to x squared minus x minus 1 at x is equal to negative 1. Okay. Now your slope of the tangent line, which they note that as just an m with tangent kind of subscripted. That's just your derivative. Which is the limit as h approaches 0, f of x plus h minus f of x all over h. Oops. Okay, now we know we're looking at x is equal to -1. So that means your slope of the tangent line is equal to the limit as h approaches 0. Instead of f of x plus h, it's f of -1 plus h. Minus f of x, we could say minus f of -1, all divided by h. So for the last example, we decided to find the derivative or the limit definition first and then plug it in afterwards, plug our value in. On this one, we're going to do it right at the beginning, which both works. Okay. So our f of -1, that's just -1 squared minus -1. Oh, let me kind of separate that a little bit. Minus 1. Make the 1 look a little more like a 1. Okay, so -1 squared is just 1. There we go. Minus -1 is plus 1. So 1 plus 1 minus 1 is just 1. So we know that f of -1 is just equal to 1. And just kind of draw a little square around that, so because we know we're going to be using it. F of -1 plus h, that's going to be -1 plus h squared. Minus -1 plus h. Minus 1. Okay, so since we're solving for an actual value, we want to know the slope of the tangent line, so we need a numerical value. We can't just leave it in this form, so we're going to have to go ahead and expand it. So -1 plus h squared, that's just -1 plus h times -1 plus h. And if we do the FOIL method, we have -1 times -1, which is +1. Your outer is -1 times h. Your inner is -1 times h. And your last is h times h. So that gives us 1. Combine those two, minus 2h plus h squared. So that means our f of -1 plus h, instead of -1 plus h squared, we can replace that with this. So 1 minus 2h plus h squared. And that minus -1 plus h, well, to get rid of those parentheses, we just go ahead and distribute. -1 times -1 is +1. -1 times positive h is negative h, so minus h minus 1. Okay. We can see automatically you have a positive 1 and a minus 1, so those two cancel each other out. You have two h terms, so we can combine those. So we have f of negative 1 plus h is equal to, that 1 is still there, negative 2h minus h is negative 3h, or minus 3h, plus h squared. Okay, so now we have everything we need to find our slope of the tangent line. So now we just plug in everything from our formula. So the slope of the tangent line is equal to the limit as h approaches 0 of f of negative 1 plus h. So that's 1 minus 3h plus h squared, minus f of negative 1. So f of negative 1 is just 1. So minus, and when it's just one term, you don't have to put parentheses, but I'll do it anyway. Just one term, you don't have to distribute anything. All divided by h. Okay, so this 1 and this minus 1 cancel each other out. That means our slope of the tangent line is the limit as h approaches 0 of negative 3h plus h squared divided by h. Okay, and just like with the difference quotient, you know you did everything correctly if the only terms left up top have factors of h. Because now all we have to do is factor out an h. Our slope of the tangent line is equal to the limit as h approaches 0. We factor out an h. That gives us negative 3 plus h divided by h. Where anything divided by itself is 1, so those two cancel each other out. So that leaves us with the limit as h approaches 0 of negative 3 plus h. Okay. Now, we couldn't do direct substitution up here at the very beginning because we had a denominator of 0. But after doing all of that, we can use direct substitution. That just gives us negative 3 and replace h with 0, so -3 plus 0, which is just -3. All right, any questions on that one? Okay, anyone still writing? Okay. Okay, so let's say if it's given that r of x is equal to 3x to the fourth power plus 4x squared plus 7x plus 4. We want to find r prime of x using, clean that s up a little bit, the limit definition of a derivative. Okay. Well, in this case, our r prime of x is equal to the limit as h approaches 0 of r of x plus h minus r of x all over h. Okay, so we already know r of x, that's given to us, so we don't have to find that. R of x plus h, it's 3x plus h to the fourth plus 4 times x plus h squared plus 7 times x plus h plus 4. Okay, so if we work this all out, you can use whatever method you like. Our x plus h to the fourth power, that's equal to x to the fourth power plus 4x to the third h plus 6x squared h squared plus 4x h to the third power plus h to the fourth power. And our x plus h squared, that's equal to x squared plus 2xh plus h squared. For x plus h to the fourth power, you can use binomial theorem. You can use, for me, it's easy to use Pascal's triangle, but either one of those will work. Or you can do x plus h times x plus h times x plus h times x plus h, FOIL two of them together, and then just distribute between those two products. So we know that our r of x plus h is going to equal 3, and that x plus h to the fourth, we can just replace with this. X to the fourth plus 4x to the third h plus 6x squared h squared plus 4x h to the third plus h to the fourth. Plus 4x squared. Actually, this is going to get lengthy, and I knew it was going to do that beforehand. So plus 4 times x plus h squared. Oh, forgot my 4. And that x plus h squared, we replace that with x squared plus 2xh plus h squared plus 7 times x plus h plus 4. Okay, so now we have to get rid of the parentheses. So here we're going to distribute that 3 to each of those terms. And here we're going to distribute that 4 to each of these terms. And we're going to distribute the 7 to those two terms. So our r of x is equal to 3x to the fourth power plus 12x to the third times h plus 18x squared h squared plus 12x h to the third plus 3x to the fourth, h to the fourth, plus 4x squared. And I'm going to go ahead and draw a little box around this. Plus 4x squared plus 8xh. And I'll just plus 8xh plus 4h squared plus 7x after we distribute the 7 plus 7h plus 4. But r of x should have been r of x plus h. I think I said x plus h, but then put r of x for some reason. Anyway. Okay, so it should be r of x plus h. I don't know why I put r of x. Okay, so that means our r prime of x is equal to the limit as h approaches 0 of r of x plus h, because we're now plugging it into this one. So that's 3x to the fourth plus 12x to the third h plus 18x squared h squared plus 12x h to the third plus 3h to the fourth plus 4x squared plus 8x h plus 4h squared plus 7x plus 7h plus 4. And I'll put parentheses around the whole thing. Okay, and that minus your r of x, which is 3x to the fourth plus 4x squared plus 7x plus 4. I know that's really lengthy. And that is all divided by h. So let me put my limit a little further down just to, and you can probably fit it all on one line, but I'm trying to write big enough so everyone can see it. But if you write small enough, you can fit it all on one line, at least all of that on one line. Okay. So now we know that this lengthy polynomial is positive, so we can drop the parentheses. But with this minus, you just have to distribute that to each of those terms. And see if I can write to get as many of them on one line as possible. So we have the limit as h approaches 0 of 3x to the fourth power plus 12x to the third h plus 18x squared h squared plus 12x h to the third plus 3h to the fourth plus 4x squared plus 8xh plus 4h squared plus 7x plus 7h plus 4 minus 3x to the fourth minus 4x squared minus 7x minus 4. And all of that divided by h. So as you can see, these can get really, really long, really, really fast. But the good news is, after this step, things should start canceling out. So if you notice here, you have 3x to the fourth, negative 3x to the fourth. You have 4x squared minus 4x squared. You have plus 7x and minus 7x. And you have a plus 4 and a minus 4. So just like before, if you did everything correctly, all the terms that don't have a factor of h should cancel out. So you should just be left with terms that have a factor of h. Okay, so this will be a little bit shorter. So the limit as h approaches 0 12x to the third h. We might even be able to fit it all on one line. Plus 18x squared h squared plus 12x h to the third plus 3h to the fourth plus 8x h plus 4h squared plus 7h divided by h. Bring it up a little bit. So on the next page, we're just going to factor out an h. Excuse me. All right, so I'm just gonna move this up a little bit. Oops. There we go. So if we factor out an h, that leaves us with the limit as h approaches 0 of h times 12x to the third power, because we factored out the h, plus 18x squared h plus 12x times h squared plus 3h to the third power plus 8x plus 4h plus 7, all divided by h. These two h factors cancel each other out. So we can see that the limit as h approaches 0 of 12x to the third plus 18x squared h plus 12x h squared plus 3h to the third plus 8x plus 4h plus 7. Okay, so now we can go ahead and apply direct substitution. So we replace every h with 0. So if we do that, we don't have to rewrite all of that with 0. We know that when we plug in h equals 0, that term is going to disappear. So if this h is 0, that term disappears. If this h is 0, that term disappears. H is 0, that one disappears. H is 0, that one disappears. Okay. So once we apply direct substitution, we don't need the limit anymore. So that just gives us 12x to the third power plus 8x plus 7. That's our r prime of x. So don't get too worried. We do have a shortcut method for this later on in the chapter. This is more of a find it using the concept of limit definitions type of problem. Okay. Because concepts are important because they show up over and over and over and over and over. So you definitely want to understand the concepts. Okay. Are there any questions on this one? All right. I'll give it up for a little bit. Let everyone finish writing. All right. Anyone still writing? Okay. So what if we wanted to find the derivative of f of t equals 2 divided by t using the limit definition? Of a derivative. Okay, so remember to find the derivative, which is our f prime of t in this case. That's just the limit as t as h approaches 0. F of t plus h minus f of t all over h. Okay, so sometimes the function variable will change. You'll see f of t, g of t, f of h, g of h. That's the only thing that changes. The concept is exactly the same, even if the variable changes. Okay, so we know that f of t, well, that was given to us, so that's 2 over t. And f of t plus h is just 2 over t plus h. So finding this one was a lot easier than finding the last one. So if we plug this in, then our f prime of t is equal to the limit as h approaches 0 f of t plus h, so that's 2 over t plus h, minus f of t, that's minus 2 over t all over h. Okay. So if you run across one like this, first thing you want to do is you want to combine these two terms in the numerator. So to do that, we just have the limit as h approaches 0. 2 divided by t plus h, we're going to multiply that by t over t, since that's the opposite denominator. So t divided by t times 2 divided by t plus h. minus 2 divided by t, we're going to multiply that by the opposite denominator. So that's going to be t plus h divided by t plus h. We're going to divide that by h. Okay, so that gives us the limit as h approaches 0. We have 2 times t minus 2 times t plus h divided by t times t plus h. We can put that all over 1 since they're the same denominator. We can put it all under one quotient. That whole thing is divided by h. Okay, so now we're just going to distribute this negative 2. We're not going to distribute the t down here. You can, but you don't have to. And I'll show you why a little bit later. So our f prime of t is equal to the limit as h approaches 0 of 2t minus 2t when we distribute that negative 2 minus 2h divided by t times t plus h. And we're not going to divide all of that by h, but what we're going to do, I made that a little too close. Let me give that a little room. Is we're going to multiply this numerator and denominator by 1 over h. So h times 1 over h is 1, so those two disappear. So multiplying this numerator by 1 over h just puts our denominator h down here. Because it's t times t plus h times h. So we can see that the 2t minus 2t, that's 0 when you add them together. So those two disappear. So we have f prime of t is equal to the limit as h approaches 0 of negative 2h divided by t times t plus h times h. We can see there that the two h factors cancel each other out. Okay, so that gives us f prime of t is equal to the limit as h approaches 0 of negative 2 divided by t times t plus h. So now we can apply direct substitution. We know that once we apply direct substitution, we don't need the limit anymore. So f prime of t is equal to -2 divided by t times t plus 0. Just replace the h with 0. Well, that's just -2 times divided by t times t. T plus 0 is just t, which is -2 over t squared. All right, any questions on that one? Anyone still writing? All right. Okay, so let's say if we are given that f of x is equal to 3 minus 8x. Find f prime of -9 using the limit definition of a derivative. Okay, so before, when we knew the value, you can call it x sub 0, you can call it a. Sometimes you'll see a, I'll use a this time. So f prime of some value that we will call a is equal to the limit as h approaches 0, f of a plus h minus f of a all over h. But remember, there was a second definition when you know the value of a. That was f of x. And it had minus f of x 0, but sometimes they call it f of a. F of a all divided by x minus a. This one right here, this is the first definition of a derivative. And this is the second definition. Oops. Make sure I put my parentheses there. Could have given myself a little more room. Let me rewrite that a little clearer. Here's the second definition. There we go. That's a little bit better. Okay. Now, when you know the value of a, like I showed before, we can use the first definition, but the second definition is a little bit easier. Okay, so f prime of -9 is equal to the limit as h approaches 0 of f of x minus f of 9 divided by x minus -9. Oh, forgot my negative here. Here we go. X minus -9. Okay. Well, finding f of -9 is not too bad, because if f of x is 3 minus 8x, we know that f of -9 is 3 minus 8 times -9. Okay, which is 3 plus 72, which is 75. So we can rewrite this as f prime of -9 is equal to the limit as h approaches 0 of f of x, which we already know is 3 minus 8x, minus f of -9, which we know is 75, all divided by x minus -9, which we can just rewrite as x plus 9. So we can go ahead and combine those two terms. Let me straighten that parenthesis up a little bit. There we go. Okay, so we know that f prime of -9 is equal to the limit as h approaches 0 of -8x minus 72 when we get 3 minus 75. We get -72 all over x plus 9. Okay. So for our numerator, we can just factor out a -8. So that equals the limit as h approaches 0 of -8 times x plus 9 divided by x plus 9. And you can always double check, distribute the -8, get -8x minus 72. Where the x plus 9 and x plus 9 factors cancel each other out. So we get the limit as h approaches 0 of -8. Well, we know the limit of a constant is just that constant. So this is just going to equal -8. Any questions on that one? Yes.
For the limit, would it be as h approaches 0, even though we aren't using the f of x plus h notation, or would we want to use the as x approaches x0 notation? Or does it matter? Or does it not matter, I should say?
Well, you could use that one, but in both cases, it's the distance between the two. But we could say as x approaches a because the distance between x and a is just your value h. So yeah, if you want to, yep, you can definitely put as x approaches a because that'll still give a denominator of 0 instead of h. So you can say x approaches a also.
Okay.
All right. Does that make sense?
Yeah.
Okay. So yeah, if you want to, you can say as x approaches a or x approaches 9 in this case, just to keep it the same all the way through. You say x approaches 9, x approaches 9, or negative 9. X approaches negative 9, x approaches negative 9, x approaches negative 9. There we go. So either h or x approaches a pretty much says the same thing. All right. Any questions on that one? All right. Okay, so we're going to go ahead and start on 3.2. Okay, anyone still writing? Okay. Okay, and this covers concepts of the derivative of a function. So if you remember, which you should because we discussed it a few minutes ago, the slope of the tangent line is just your first derivative, which is the limit of f of x plus h minus f of x all over h as h approaches 0. Or when we know the value of a, or you can call it x of 0. I just think a is a little easier to deal with than all the subscripts. Then f prime of a is equal to still the slope of the tangent line, which is the limit of f of a plus h minus f of a all over h as h approaches 0, or you can do a plus h minus a, which is still just h. Now, also, there was a reason we went over the linear slopes. So if a line goes up and to the right, it's a positive slope. Because your slope m is greater than 0. Let me kind of separate that. And if it goes down and to the right, it's a negative slope. So your slope m is less than 0. And it is just a horizontal line. Say horizontal or constant slope. Where the rate of change is equal to 0. Remember, these are for y is equal to mx plus b. All right. Anyone still writing? All right. Okay, so let's say, for example, if we have just a graph. And I'll write it out large enough. Let's say our graph just looks like that, where our y-axis is somewhere around here. Okay, so let's say for around this point of the graph is above x equals -2. And right here at the top of this curve, let's say that's where x is equal to -1. Let's say at this point here, that's at +1. Probably could have moved that over a little bit more, but let's say at this point here, x is equal to 3. And let's say at this point right about here, we make x equal to 5. Okay. So let's look at x equals -2. If we had a secant line at any point, and we moved it closer and closer and closer and closer and closer to that one, we'd have a tangent line that looked like this. We kind of touch it at just that one spot. So because it's going up and to the right, we know the slope of that tangent line is positive. Or you can just say that f prime of x is positive. Okay, so we know that at x equals -2, we know that f prime of -2 is greater than 0. So when the derivative is greater than 0, we could see that our graph is increasing. F of x is increasing at x equals -2. Well, let's look at x is equal to -1, right at there at the peak. Okay. So if we did the secant line and moved it closer and closer and closer and closer and closer, our tangent line slope would kind of look like this. Okay. So the slope is horizontal, so we know that is equal to 0. So if the slope of the tangent line is 0, that means your f prime of x is equal to 0 whenever you have that horizontal tangent line. So that tells us that at x equals -1, f prime of -1 is equal to 0 because you have a horizontal constant slope at x equals -1. Okay. Goes right back to the function, the linear function, where you have up and to the right, it's positive, down and to the right, slope is negative. Same thing here. Up and to the right, it's horizontal, it's 0. This point here, that slope of the tangent line would be down and to the right. So we can see at x equals +1, we see that the slope of the tangent line at 1 is less than 0. So we can see whenever the slope of the tangent line is less than 0, it's decreasing at that point. Okay. Same thing at x equals 3. You look at the slope of the tangent line, you see that it would be going somewhere like this. Oh, forgot to put my f prime of x is less than 0 for right here. Okay. So we can see that at x equals 3, the slope of the tangent line is positive. So f prime of x is greater than 0. So at x equals 3, f prime of 3 is greater than 0. So So we know that f of x is increasing at x equals 3. Uh-oh. There we go. Bring that down. There we go. Okay. Same thing at x equals 5. You can see our slope of the tangent line kind of going down and to the right. So since our slope of the tangent line is going down and to the right, we know that our derivative at that point is less than 0. We know at x is equal to 5, f prime of 5 is less than 0. So the fact that it's less than 0 lets us know that f of x is decreasing. At x equals 5. Okay. Any questions on this one? All right. Anyone still writing? Okay. Okay. So let's say, for example, that suppose that a piecewise function is f of x is equal to 1 minus 2x for x is less than or equal to 2, and negative 3x squared plus 10x minus 11 when x is greater than 2. Which of the following statements are true? Okay, is or are. Could be one, could be more than one. Okay. So let's say for A, f is neither differentiable or continuous. At x equals 2. Or f is continuous but not differentiable. And differentiable, let's write the shortcut version of that. At x equals 2. or f is both differentiable and continuous at x equals 2. Okay, so if we remember, f of x is continuous at x is equal to c if and only if. You might see that every once in a while. It just means if and only if, which makes no sense to me, but seems a little redundant, but that is a notation they use. So if you see IFF, it's not a typo. It actually means if and only if. Okay, so the first condition was that f of c is defined. Remember, the second condition is the limit of f of x as x approaches c exists. And the third condition is that the limit of f of x, excuse me, as x approaches c is equal to f of c. Okay, but we're going to use the shortcut version of it that you kind of saw at the end. We know that f of x is continuous at x equals c if and only if we know the limit of f of x as x approaches c from the left is equal to the limit of f of x as x approaches c from the right, and they're both equal to f of c. Make that a little clearer. This basically combines all three of those steps. So again, just as a quick visual, we'll draw out our number line. From negative infinity to infinity. Okay, we know with this problem, our constraint pretty much revolves around 2. Okay, so we'll make 2 our critical point. So the first constraint is that x is less than or equal to 2. And we know when x is less than or equal to 2, our f of x is equal to 1 minus 2x. The next constraint is x is greater than 2. We know when x is greater than 2, our f of x is negative 3x squared plus 10x minus 11. Okay, so using the shortcut, first I have to find the limit of f of x as x approaches c from the left, which would give us this one right here. Okay, well, in this case, c is equal to 2, so we can just say as x approaches 2 from the left. So when you're approaching 2 from the left, you're coming in this direction. So your f of x is 1 minus 2x. So that's equal to the limit of 1 minus 2x as x approaches 2 from the left. Okay. We can just go ahead and use direct substitution. That's just 1 minus 2 times 2, which is negative 3. Same thing here, but we have to find the limit of f of x as x approaches 2 from the right. Okay. We can see that from the right, if you're approaching 2, your f of x is negative 3x squared plus 10x minus 11. So that's the limit as x approaches 2 from the right of negative 3x squared plus 10x minus 11. So again, if we use direct substitution, you have negative 3 times 2 squared plus 10 times 2 minus 11. Okay, so here we have 2 squared, which is 4 times 3, so that's negative 12 plus 20 minus 11. Hold on. Negative 12 plus 20 minus 11. So negative 20 plus 12 is positive 8. 8 minus 11 is negative 3. There we go. Okay, so we see the limit from the left is equal to the limit from the right, and they're both equal to a value f of c. Well, in this case, f of 3. I mean, f of 2, which equals negative 3. Okay, so we can see that f of x is continuous. At x equals 2. So we know it's not A, so it's either B or C. All right, any questions on that one? All right. Okay, so now we have to check and see if it's differentiable. So we want to know is f of x differentiable at x equals 2. All that means is that does the derivative exist? At x equals 2. Okay. Now with this one, we have pretty much the same concept of the steps, because we know that f prime, or the derivative at some value a exists when the derivative or the limit of f of x minus f of a all over x minus a as x approaches a from the left is equal to the limit of f of x minus f of a as x approaches x minus a, as x approaches a from the right. X minus a as x approaches a from the right. So the concept is pretty similar to continuity. Okay, so let's find the limit as x approaches 2 from the left. Okay, so we have the limit x approaches 2 from the left of f of x minus f of 2, all divided by x minus 2. Okay. Well, honestly, we don't even have to do that because we plugged in 2 from the left. We already know it's equal to -3. So that f of 2 right there, we can just replace that with -3. So our f of x, oops, got to get that off the previous page. There we go. So your f of x from the left is 1 minus 2x. So you're approaching 2 from the left. So that's your limit as x approaches 2 from the left. 1 minus 2x minus -3 divided by x minus a, or x minus 2. I'm going to need this again, so I might as well leave it there. All right, so let me write a little side note for that one. F of x equals 1 minus 2x as x approaches 2 from the left. Okay, so we can get this minus negative and just make it plus. So the limit x approaches 2 from the left. 1 minus 2x plus 3 all over x minus 2. If we go ahead and combine the 1 and the 3, we get the limit as x approaches 2 from the left of negative 2x plus 4 divided by x minus 2. Okay. Now in our numerator, we can actually factor out a negative 2. That gives us the limit as x approaches 2 from the left of negative 2 times x minus 2 all over x minus 2. Of course, the x minus 2 factors cancel each other out. So we see that the limit as x approaches 2 from the left of negative 2 is just negative 2, since the limit of a constant is just that constant. Okay, and we do the exact same thing for the limit from the right. And if that turns out to be negative 2 also, then it's differentiable. If it's a number other than negative 2, then it's continuous but not differentiable. So we're going to take the limit as x approaches 2 from the right of f of x minus f of 2 divided by x minus 2. And that's going to, we can rewrite that as a limit as x approaches 2 from the right of f of x. Now from the right, let me make that a little bit bigger. Okay, now from the right, f of x is equal to, there we go, negative 3x squared plus 10x minus 11. We are approaching 2 from the right. Negative 3x squared plus 10x minus 11 as x approaches 2 from the right. Let me move this over, make sure, because it looks like I might run out of room. So I want to make sure I have enough room before I start writing. Okay, so the limit as x approaches 2 from the right of f of x, so negative 3x squared plus 10x minus 11 minus f of 2, which we already know is negative 3. So minus negative 3, all divided by x minus 2. All right, so let's go ahead and simplify this. We have the limit as x approaches 2 from the right of negative 3x squared plus 10x minus 11. This polynomial is positive, so we can go ahead and drop the parentheses. Negative 3x squared plus 10x minus 11 minus negative 3 is plus 3 divided by x minus 2. Okay, so we can go ahead and combine the two constants. So you have the limit as x approaches 2 from the right of negative 3x squared plus 10x minus 8 all over x minus 2. Okay. We can actually go ahead and factor your numerator. And you can use the quadratic formula, A times C method, whichever method you like. Okay. So you have the limit as x approaches 2 from the right. If we factor that, we'd end up with negative x minus 2 times 3x minus 4 divided by x minus 2. I can put parentheses around this one. Where, of course, the x minus 2s cancel each other out. That's equal to the limit as x approaches 2 from the right of negative 3x plus 4. 3x minus 4. You could distribute it if you want to and make it negative 3x plus 4, or you can leave it factored like that. So now we can use direct substitution. We couldn't do it up here, but we can do it down here. So that's negative 3 times 2 minus 4. Okay, 3 times 2 is 6. 6 minus 4 is 2. So that's negative 2, or just negative 2, which is the same as the derivative from the right. Okay, so we can see that our function f of x is continuous and differentiable. At x equals 2. So the answer for that one would be C. Okay, are there any questions on that one? So again, for continuity and differentiability, you're just approaching from the left and the right. So there's a little bit of a connection there. Okay, anyone still writing? All right. Okay, so what if we wanted to find the values of A and B that makes the following piecewise function both continuous and differentiable? Okay, so what if our piecewise function is f of x is equal to 5x minus 1 when x is less than 5, and negative 2x squared plus ax plus b when x is greater than or equal to 5. Okay. So again, for continuity, we just have to remember that f of x is continuous at x equals c when the limit of f of x as x approaches c from the left is equal to the limit of f of x as x approaches c to the right, and they're both equal to some real value f of c. So again, that's just all three steps all three conditions in one step. Well, not one step, but in one equivalent equation. So again, whenever dealing with a piecewise function, I always draw out my number line. Okay. So our constraints revolve around 5. So we know that's our critical number. Or our constraint value. I won't say critical number. Okay. So we know that this interval is our x is less than 5. And when x is less than 5, our f of x is equal to 5x minus 1. And we know this interval here, that's our x is greater than or equal to 5. And for x is greater than or equal to 5, we know that our f of x is equal to negative 2x squared plus ax plus b. Okay, so now we have to find the limit of f of x as x approaches c from the left. Or in this case, the limit as x approaches 2 from the left. Not 2, 5 from the left. Thinking of the last problem. Limit of our f of x. Well, in this case, as you approach 5 from the left, our f of x is 5x minus 1. So that's the limit as x approaches 5 from the left of 5x minus 1. So again, if we use direct substitution, that's just 5 times 5 minus 1, which is 25 minus 1, which is 24. Okay. Now we have to take the limit of f of x as x approaches 5 from the right. Well, as you approach 5 from the right, this is your f of x. So this is the limit of negative 2x squared plus a times x plus b as x approaches 5 from the right. So again, we use direct substitution, but we can only substitute the x. That's negative 2 times 5 squared plus a times 5 plus b. Okay, so if we simplify this, 5 squared is 5 times 5, which is 25. 25 times negative 2 is negative 50. So we get negative 50 plus a times 5. We can rewrite that as plus 5a plus b. Okay, so that's the limit of f of x as you approach 5 from the right. Now, for these two to be continuous at that point 5, the limit from the left and the right has to be the same. So that means negative 50 plus 5a plus b has to be equal to 24. So if we go ahead and add 50 to both sides, those two cancel out. So that means 5a plus b has to be equal to 24 plus 50, which is 74. So we're going to come back to this. We're just going to leave this for now because it's going to be useful later. And I'll start the other part on the next page. Kind of running out a little bit. All right. Anyone still writing? Okay. Okay. Now the same thing with differentiability. So we know that f of x is differentiable at x equals c if the limit of f of x minus f of c divided by x minus c as x approaches c from the left is equal to the limit of f of x minus f of c all over x minus c as x approaches c from the right. And they both equal f prime of c. So again, the process for differentiability and continuity are very closely related. Okay, let's look at the limit as x approaches 5 from the left of f of x minus f of 5 all over x minus 5. So if we go back to the previous page, we can see that we already know what the value is when you plug in 5 from the left. That's just 5 times 5 minus 1, which is 24. So we already have that f of 5 from the left. So f of 5 equals 24 from the left. Okay, and we know from the left our f of x is 5x minus 1. Okay, so we know that also. So that's the limit as x approaches 5 from the left of 5x minus 1 minus 24, which is our f of 5, all divided by, let me make that negative a little bit clearer. 5 from the left, there we go. X minus 5. Okay, well, we have 5x minus 1 minus 24. Go ahead and combine these two. That's 5x minus 25. So we can just rewrite that as the limit as x approaches 5 from the left of 5x minus 25 divided by x minus 5. Okay, so we can go ahead and factor this numerator. Which gives us the limit as x approaches 5 from the left of 5 times x minus 5 all over x minus 5. Well, we can see that anything divided by itself is always going to give us 1. So this just becomes the limit as x approaches 5 from the left of 5, which is 5. Okay, so we're done with this part as x approaches 5 from the left. Okay, now we have to find the limit as you approach 5 from the right, and that's where we have our unknowns. So limit of f of x minus f of 5 all over x minus 5 as x approaches 5 from the right. Okay, so we see as x approaches 5 from the right, our f of x is negative 2x squared plus ax plus b. And our f of 5 is still, where is it? 24. Nope. Actually, nope. Uh-oh. From the right, it's right here. I'm looking at the wrong one. So this is your limit from the right. There we go. Okay, So that gives us the limit as x approaches 5 from the right of negative 2x squared plus ax plus b. Okay. Now, before we combine them, we had it just in the form of negative 50 plus 5a plus b. So actually make a correction. I meant to write it up under that one. So I do want to erase that and put that up here. So this is your limit from the right. I should have drawn a line, which is why I do that, just to avoid errors like that. So this is your limit as x approaches 5 from the right. X approaches 5 from the left. Yeah. So whenever possible, just draw a line separating your steps. And say when everything kind of runs together, it's really easy to write down something completely different than what you intend to. Okay, that's all over x minus 5. Okay, so if we go ahead and distribute that negative, that's the limit as x approaches 5 from the right of negative 2x squared plus ax plus b plus 50 minus 5a minus b all over x minus 5. Okay. Now this is the helpful part because you have plus b and minus b. So that b disappears. We can always go back and solve for it, but it helps us because now we only have to worry about the a. So if we have the limit as x approaches 5 from the right of negative 2x squared plus ax plus 50 minus 5a. All over x minus 5. So now all we have to do is factor our numerator. And to factor that, I'll just show the steps right here on the side. Give that a little more space. Here we go. Okay, so we start off with negative 2x squared plus ax plus 50 minus 5a. Okay, so we have 4 terms. We want to factor them. So whenever you have 4 terms, the first thought I have is factor by grouping. Okay, but what we want to do, we're going to rearrange this a little bit because we want the 2 a terms next to each other so we can factor out that a. Okay, so we have negative 2x squared plus 50 plus ax minus 5a. We're going to factor those two terms, or those two subgroups. So the negative 2x squared plus 50, we can factor out a negative 2. And that'll leave us with x squared minus 25. Yep. And for these two, we can factor out an a. Let me make that a little bit clearer. There we go. We can factor out an a, and that leaves us with x minus 5. Okay. Now, x squared minus 25, that's the difference of squares. So we can factor that a little bit more. See if I can fit this over here. So we have negative 2 times x minus 5 times x plus 5 plus a times x plus x minus 5. So we worried about squeezing it in there. X minus 5. There we go. Okay. So now we can factor out x minus 5 from both of those. So if we factor that out from both of those, in the parentheses, our first term would be negative 2 times x plus 5, and it would be a. I'll just switch those around and make it a minus 2 times x plus 5. So if we distribute that negative 2, that gives us x minus 5 times a minus 2x minus 10. So this is the limit as x approaches 5 from the right, replacing all of this up here with x minus 5 times a minus 2x minus 10, all divided by x minus 5. And again, this is just factor by grouping. Okay, so you can see that the x minus 5 factors cancel each other out. So we have the limit as x approaches 5 from the right of a minus 2x minus 10. Okay, and if we use direct substitution, that just leaves us with a minus 2 times 5 minus 10. Oops, don't really need the in parentheses. Okay, so negative 2 times 5 is negative 10. Negative 10 minus 10 gives us negative 20, so we have a minus 20. Okay. So we know that the limit as you approach 5 from the right has to be equal to the limit as you approach 5 from the left. These two has to be the same. And we'll continue that on the next page. Leave it up for a little bit. All right, anyone still writing? Okay. So I'm gonna need this anyway. I'll put it right up there. Okay, so we know that to be differentiable, a minus 20 has to equal 5, which is what we have here. Those two have to be equal to each other. So we add 20 to both sides, so we know that a has to equal 25. Okay. Now we have to solve for b. To do that, we go right back to that one we were going to leave for right now. So we know 5a plus b has to equal 74. Okay. Well, we know a is equal to 25. So 5 times 25 plus b is equal to 74. Okay. So 5 times 25 is 125 plus b equals 74. So if we subtract 125 from both sides, b is equal to negative 51. Okay. So in order to be continuous and differentiable, we'd have to make this negative 2x squared plus 25x minus 51. Then it would be continuous and differentiable at x equals 5. Now, if you want to change it for x equals 4, x equals 3, x equals 2, you'd have to go through the whole process again. But at x equals 5, we know it's continuous and differentiable if we use a and b for those two values. All right, any questions on that one? All right, so we'll go ahead and stop there. Okay, so remember there's no class on Monday. So don't do like I've done a couple of times, drive up and see you're the only car in the parking lot. So, not only one, but one of the few. All right, so if you have questions, of course, feel free to ask away. If not, I will see you on Tuesday.
Have a good weekend.
All right, you too.
So yesterday I tried opening the videos on multiple different devices,
Mhm.
and it keeps popping up with this. Like I tried my phone, my iPad, my laptop, and each one is like this. It's not just that one.
It's mentioning cookies. That I'm wondering.